Our final topic in Unit 3 is RC circuits, which is basically just a circuit that has at least one resistor, at least one capacitor, and some EMF source. You'll see on the slide here multiple different examples of RC circuits, and while each one of these looks different, it does meet those minimum requirements. That circuit that you see on the top left, where it has a switch between A and B, is our simplest RC circuit, and that's the one we're going to focus on analyzing. When that switch is set to point A, we consider that to be the charging circuit for the capacitor. And once that capacitor is fully charged, if we move that switch to B, then our capacitor will discharge through that resistor. So let's focus on that idea of charging here. Our goal for the majority of this video is going to be to derive an expression for the charge on the capacitor at a time t after the switch has been closed and been closed on A. So in other words, we're going from having this capacitor that's completely uncharged to having this capacitor that is slowly building up charge, because it's not an immediate thing, the way that the capacitor builds up charge. And so the first thing we're going to do is apply one of the most useful rules in circuits, and that is Kirchhoff's loop rule. So we know that the loop rule tells us that the potential difference around any loop in our circuit is equal to 0. And I'm going to follow this loop rule going clockwise around my circuit. So I have the EMF of the battery, and I'm going clockwise, so I'm going from the negative to the positive, so that's a positive EMF, minus the voltage across the resistor, because I'm traveling through that resistor in the same direction current travels through it, and so we know that that's a negative potential difference, and then minus the voltage across the capacitor. To understand why that that voltage across the capacitor is a minus, we're going to think about what's actually happening in my circuit. I have electrons coming from the battery, and they're going to come along the circuit, and they're going to go up to that bottom plate of my capacitor. Now, electrons can't travel through the gap in the capacitor, so I'm going to end up with a bunch of extra electrons on this bottom plate, and a bunch of extra, when an electron goes on the bottom plate, it then is going to kick off some electrons that are on the top plate. So the top plate will become positive, and that bottom plate will be negative. And so as I'm traveling in my loop going clockwise, I'll be going from the positive to the negative, so it's a negative potential difference there. Now, I am going to replace each of these potential differences with their respective equations, using Ohm's law for the resistor and using our equation for capacitance to find the voltage across that capacitor. Now, as time increases, I know that my current will not be constant, because as the charge builds up on the capacitor, the electrons will be less and less attracted to that bottom plate. As a matter of fact, they'll slowly get to the point where they're getting more repelled from that bottom plate. And so the current will not be constant. Also, the charge on the capacitor is not constant. It's building up over time. So I need to find a way to have only one variable in this equation. And right now, both current and charge are not constant. So I'm going to use the fact that I know that current can be expressed as dq dt and put that in place of current. And now I only have one variable, that q. And as a matter of fact, I now have a differential equation. So many times when we see RC circuits on the AP test, a portion of that AP test will be to write a differential equation for our circuit. And the key there is using the loop rule and then using the fact that current is equal to dq dt. Now, writing that differential equation is not enough. We also need to solve it. So you'll see the same differential equation written here. The only thing that I've done is I've moved one of the terms to the other side of the equation. Our first step in solving this differential equation is to separate our variables. So I'm going to have dq dt all by itself, and notice that I've divided every single term by r. Now I'm going to find a common denominator to make it easier for me to separate those variables. So that common denominator is r times c, and then you'll see what that numerator looks like. And then separation of variables means we get dq on one side and dt on the other. Because my numerator, that EC minus Q, has a Q in it, I want that to be on the same side of the equation as the DQ. And then that RC, you could leave there, but I find it easier to put that with the DT. So now I've successfully separated my variables, which means it's time for the calculus. We have to take the integral of both sides. Oops, sorry, a little too far there. And doing the integral is going to require me to do some u substitution here. So I'm going to let u be equal to EC minus Q, and then du is negative dq. And so my integral then becomes negative 1 over u du. And on the right-hand side, I went ahead and actually took that integral. I'm going from time equals 0 to time equals t. And r times c, that's a constant. So I can pull that out of my equation. So I was basically left with 1 over rc times the integral of dt, which we know is just t. So that's where that right-hand side came from. For my left-hand side, I'm going to take that integral, and hopefully you remember from calculus class that the integral of 1 over u du is the natural log. And since there's that negative sign, I pulled that out before I actually took the integral, and you could really move that negative sign to either side of the equation. Next, I want to go ahead and plug back in what u is equal to and then evaluate it with my limits, 0 to q. I forgot to mention this at the start of this video or at the start of this process, but we're using a little q here because this capacitor is not fully charged. A lot of times we use a capital Q with capacitors when it's fully charged and a little q to represent the charge as time increases. So plugging in those limits, I end up with the natural log of EC minus Q. That's what I get when I plug in Q. And then when I plug in 0, I get the natural log of E times C. Now, natural logs have these wonderful properties where we can change a subtraction into a division. So you'll see I changed that into being EC minus Q divided by EC. And then we want to solve for Q because that's the whole point of this process, is finding an expression for Q as a function of time. So when we have a natural log, to undo that natural log, we use our e to raise to that power. So my left-hand side just becomes EC minus Q over EC, and the right-hand side becomes e to the negative t over RC. And then again, I'm just doing some algebra to eventually solve for Q. Commonly, we write it as EC times the expression 1 minus e to the negative t over RC. Now, as with all of the differential equations that we've done, that's a lot of work to solve that differential equation. If it's something you understand, those can be easy points if you have the time to do it. But having some basic understanding of the general form of this differential equation will get you the majority of the way there. You should at the very minimum be able to write that differential equation. And you should understand what happens when the t is really, really small and also when t is really, really large. So those are kind of our limiting factors on this. We'll talk about that in a moment. But I want to also point out that once we know the charge across a capacitor as a function of time, we can also write an expression for the voltage of the capacitor as a function of time, because we know voltage is just charge divided by capacitance. And pointing out that both of these graphs are exponential with the e to the negative t over RC quantity. So what will happen is those graphs will increase rapidly at first, and then level off, especially that charge. Eventually we get to that point where there's a total amount of charge, or kind of a set value there. RC, the resistance times the capacitance, is something known as the time constant. It is the amount of time that it takes for the capacitor to charge to, I believe it's about 63%. And basically, in general, we talk about the time constant giving us a good picture of how long it takes to charge the capacitor. I think technically, often it's considered that 5 time constants would give you a fully charged capacitor. Also, when we're thinking about what happens when time is really, really large, we end up basically getting E times C, because if you think of making that T in that equation really big, E to the negative really big number is basically going to be 0. So that charge in the capacitor is equal to the EMF of the battery times the capacitance. The reason this would happen is because once we have a fully charged capacitor, no more current can flow, and that means that the voltage across your resistor is going to be 0, since it won't have any current flowing through it. When time is equal to 0, a capacitor basically acts like a wire, offering pretty much no resistance, and so you can almost pretend like the capacitor's not there at the very beginning. So these two kind of end behaviors are really common questions on the AP exam. So you may see a question that says, immediately after switch S is moved to A, what is the current in the circuit? And if you were to see a question like that, you would just treat that capacitor as if it were a wire. And then this is a really simple circuit with just one battery and one resistor. There may be a part B that would say something like, a long time later, what is the current in the resistor? And of course, then your answer would be that the current in the resistor is 0. So again, understanding what happens. Biggest takeaway from this entire video is that when the capacitor is initially uncharged and we connect it to a charging circuit, like we're doing here by moving the switch to A, it acts as if it's a wire with no resistance. A long time later, it acts as if it's an open switch, making it so that current cannot travel through that portion of the circuit that it's on.